As we move into thinking about the hydrogen atom, we have a very heavy nucleus at the center of what we know is some sort of an electron cloud around it. And so it's going to be natural to think about the hydrogen atom in spherical coordinates. And you've probably run into these before, but I'll just go ahead and do a quick reminder. If we can convert between Cartesian XYZ coordinates and spherical coordinates r, theta, phi, using just some simple conversions. X is r sine theta cosine phi, y is r sine theta sine phi, and z is r cosine theta. So we can think of z is r, the radius, times the projection along this, the z-axis. So theta is our distance from the z-axis here, and phi is our rotation along that xyz plane, so how far we are rotated from x towards y. Thinking about this in a system that we might be familiar with, more familiar with, we could think of if z is the North Pole, theta is the declination of our vector relative to the North Pole, and phi might be where our object is relative to, say, some arbitrary point like Greenwich Mean Time. So when we're thinking about quantum mechanics in spherical coordinates, we might need to do things like normalize a wave function or otherwise perform an integral in spherical coordinates. Now, when we normalize a wave function, right, we know the Born interpretation of the Schrodinger equation tells us that psi squared is, or psi star psi, is the probability of finding a particle with that wave function psi within some infinitesimal volume dV. Now, in Cartesian coordinates, this is pretty straightforward. We can create a sort of a box or a cube anywhere in three-dimensional space, and we can perform a triple integral dx dy dz to determine its volume, and therefore perhaps the probability of finding a particle in that tiny volume of space. Now, in spherical coordinates, we have to be a little bit more careful, because if we think about some region in space, some box like this, expressed in spherical coordinates, it might span some angle of inclination and angle around the equator and some thickness. But because dr, right, this is some distance away from the equator, this area carved out is going to get bigger the further we are from the equator. So the length of this side of our kind of box shape here is going to be given by r sine theta d phi. So the further we are from the equator, or sorry, from the center of the Earth, the larger this side of the box is. Same thing with this side of the box. This is given by, the length of the side of the box is given by r d theta. And so if we want to figure out the volume of this infinitesimal box that we've sort of drawn maybe on the surface of the Earth, in spherical coordinates, we need to think about, we can't just perform an integral over dr d theta d phi. We need to take into account how far this is from the center of the Earth. That infinitesimal volume, right, if this has sides dr d theta and r sine theta d phi, then the infinitesimal volume is given by the product of the lengths of each side. So that dv volume is going to be r squared sine theta d phi. And performing an integral of any function in 3D space, we're going to need to actually use this as our dv term. And so when we perform an integral, say over all of the area of a sphere for some distance away from the origin, we're going to perform that integral. We're going to integrate all of the xyz plane. So 0 to 2 pi defines that whole circle. And we're going to need to take that circle and rotate it all the way up to the z-axis. And that'll give us our volume element. And then we're going to need to integrate that over the radius of our sphere. And keeping in mind that our dv term in spherical coordinates is r squared sine theta d theta d phi, we need to keep those terms in our integral as we perform that integral in 3D space. So a volume integral of some function over all angles from the center of the sphere to the length of the radius, which we'll just call a, right? So out to whatever the radius of the Earth is, perhaps. We have integral 0 to a r squared dr, 0 to pi sine theta d theta, 0 to 2 pi d phi, all acting on our function. And if our function is, let's just say 1, this gives us the radius of a sphere. So integral of 0 to 2 pi of 1 d phi is 2 pi. Integral of 0 to pi of sine theta is 2. Integral of 0 to a of r squared, this becomes r cubed over 3, evaluated from 0 to a, so a cubed over 3. So this gives us the formula for the volume of a sphere, 4/3 pi r cubed, where the radius is this variable a. And the last thing that I want to introduce, just because it's important to note here, is the concept of a solid angle. And we can think of the solid angle as sort of the angular portion of the surface of a sphere. And this is sort of the area of the sphere of some, we're just considering the area here rather than the total volume. So that infinitesimal area on the surface of the sphere is given by sine theta d theta d phi. And so one way that you could think about it is if you're standing at the very center of the Earth, and let's pretend that the Earth is transparent for this analogy, and you were to look out at something on the surface of our transparent Earth, the solid angle would be how big that object appeared to you, right? How much of your field of view is this object taking up? That is what solid angle means. And so we can calculate, let's say, solid angle of the entire surface of a sphere, right? If you were standing in the middle and you looked all around in all directions, how much does that sort of take up as a solid angle or as a field of view? So we would perform this integral over all two-dimensional space, sine theta d theta d phi. We're going to do 0 to 2 pi d theta, 0 to pi sine theta d theta. That gives us 4 pi. The units on this are officially steradians, and so if you were to look around in all directions, that solid angle would be 4 pi. And so some little speck like this will have a solid angle that is a small fraction of 4 pi. So we'll use a lot of these ideas as we move forward into talking about, in the next chapter, the hydrogen atom, spherical coordinates, and thinking about wave functions of a hydrogen atom in these sort of very natural coordinate systems of spherical coordinates.